Okay, calculate the change in potential energy of the satellite as it moves from the closest to the furthest point from the Earth. All right, so again, we just want to calculate, well, we need to do it the same way. We need to find the area under our graph. So we need to count the number of squares and work out what each square is worth. There's a lot more squares this time. 75. Oh, very nice. 75. I'll take 75 because I don't want to count them. All right. So let's say 75 squares. What do we have to do now? We want to work out what each square is worth. Okay. So the vertical would be, that's nice and easy. Vertically, it's just 1. 0.2 horizontally, I like that. Yeah, oh yeah, good point. Okay, so each square then, the area of each square is going to be 2 times 10 to the 5. Or you could just put 0.2 times 10 to the 6. Doesn't matter. Either way's right. So there's our area. 2 times 10 to the power of 5. We need to multiply that by the number of squares. And I get 1.5 times 10 to the 7 joules per kilogram. So our area under the graph is 1.5 times 10 to the power of 7 joules per kilogram, but we want the total change in potential energy. So we need to multiply by the mass of the object. How heavy is the satellite?
1,500 kilograms.
1,500 kilograms. So we need to multiply that by 1,500. And we will get 2.25 times 10 to the power of 10 joules. Okay, so this number over here, this 1.5 times 10 to the 7, that's the change in energy for each kilogram of our satellite. So every kilogram of our satellite has this much change in energy. So to find the total change of energy of the satellite, you need to multiply this number by the mass. Okay, so anytime you're given a gravitational field strength, that's what you need to do, a gravitational field strength graph. Okay, you need to multiply by the mass. Okay. So the satellite was moving with a speed of 15 kilometers per second at its closest point to the Earth. How fast was it traveling at its furthest point? Okay. This is a nice little question. So, there's our Earth. There's our satellite's path. Our satellite is here. And at its closest point, it's 15 kilometers per second. We want our speed over here. Okay? Now, as it gets to this point, okay, basically, its gravitational potential energy has to increase to move it further away. So what's going to happen to the speed? It'll decrease. Okay? It has to use its kinetic energy to get it out to that potential energy. So what we need to do to solve this problem is find out how much kinetic energy it takes to get from here to here. It loses that amount of kinetic energy, and so whatever's left, you can work out the speed from. Okay? So first thing we need to do is work out the kinetic energy here. So the kinetic energy of the satellite at its closest point times 1,500 times, and remember, what does V have to be in? Meters per second. So 15,000 squared. 0.5 times 1,500 times 15,000 squared. And I get 1.69 times 10 to the 11 joules. So that's the kinetic energy at this point. Okay? That's the kinetic energy here. Now, we found out earlier that as the satellite moves from its closest point to the furthest away point, we have 2.25 times 10 to the 10 joules change in gravitational potential energy. So 2.25 times 10 to the 10 joules of energy must be lost from our kinetic energy. It needs to convert this amount of energy from this to get further away. Okay? So what we need to do is subtract the amount of energy it loses from this. Okay? I know, confusing, right? So let's go through this again. From this point here to this point here, there is that much change in gravitational potential energy. Okay, we'll work that out in part A. Calculate the change in potential energy of the satellite as it moves from point A to point B. So as it moves from here to here, we get an increase of that much potential energy. That energy can't be created from nowhere. Okay? First law of thermodynamics. That energy has to come from here, the kinetic energy. So it has to donate some of its kinetic energy to get out to that gravitational potential energy. So from its kinetic energy, it needs to take 2.25 times 10 to the 10 of that to give it that gravitational potential energy. So to work out its final kinetic energy, we take this, its initial kinetic energy, and subtract what it has to give away to get to that gravitational potential energy. Okay? So, its kinetic energy at point 2, let's call this point 2, this is point 1, it's going to be equal to 1.69 times 10 to the 11 minus 2.25, oh, what's happened to my pen? Times 10 to the 10. Okay. And you should get about 1.47 times 10 to the 11 joules. So this is the kinetic energy at point 2. Okay? At point 1 it had this much kinetic energy here, 1.69, but some of that kinetic energy has to change to gravitational potential to get it out that far. So what's left is that amount of kinetic energy. Now, given amount of kinetic energy, you guys should be able to work out the speed. Yeah. This one? Yeah. 11. Sorry. I'll make that a bit clearer. 10 to the power of 11. Yeah, sorry, this one up here is 10. Yeah. Okay, so this is its kinetic energy. We should be able to convert that to velocity. Okay, so if we rearrange our kinetic energy equation, you'll get that. So our velocity is equal to the square root of 2 times 1.47 times 10 to the 11 over the mass of the object is 1500. I need to work that out. And so, yeah, you should get about 14,000 meters per second. Close to that, I've got 13,976. But 14,000 The original one was put into kilometers per second, so it's kind of nice if we do that with this one too. So there's your answer, 14 kilometers per second.